Okay, next we're going to look at a class of problems that are called elevator problems. And that involves understanding how the forces work when you're in an elevator that's either accelerating upward or accelerating downward. But first we want to consider a situation where the elevator is not accelerating at all. So it's moving at a constant velocity. And that could be a velocity of 0. It could just be sitting there, but it could also be going at, 3 meters per second up or 3 meters per second down, just not accelerating. Now, what we want to do, I've got a picture here. This is the elevator that you can see. And we've got a person, and they're standing on a bathroom scale in the elevator. Of course, I always like to take a bathroom scale into my elevator when I go on a ride, so you probably like to do the same thing. So you've got your bathroom scale on the floor of the elevator, and you're standing on it. And the elevator is moving upward or downward, but it's not accelerating, or it's just sitting there. And the question is, what's the normal force going to be? And why do I care about the normal force? Well, we've mentioned previously that's what the scale is going to read. If you push down on the scale with a certain weight or certain force, the scale is going to read that force, and that's the force that the scale is going to push back with. So if we want to know what the normal force in this situation is, we just have to solve for it. So here is our elevator. Again, our acceleration is 0. We've got a free body diagram off to the side. All the forces are in the y direction. We have the normal force pointing up, the weight pointing down. And so we can do the sum of the forces, or the normal force minus mg. That's equal to 0 because there's no acceleration in the y direction. And solving for the normal force, we get that the normal force is just the weight. Now, what happens to the normal force if the elevator actually does have an acceleration? And we'll take the case of the acceleration pointing up. Now, again, we're simply going to apply Newton's second law. The sum of the forces equals ma, and then we'll solve for the normal force. And so we'll do Fn minus mg equals ma, which we can see here. So I've got the sum of the forces, and all these forces are, of course, in the y direction. The normal force minus the weight equals mass times acceleration. I can take my normal force and solve for it. I move the mg over there, and I get that the normal force is ma plus mg. I can factor out an m because there's an m on each term, and that gives me the normal force is ma plus g, m times quantity a plus g. Now, the normal force, when the elevator is not accelerating, when a is equal to 0, you get the normal force is equal to m times little g. So what's effectively happening, it's like gravity is being increased. So when the elevator is accelerating upward, you'll actually get a bigger reading on the scale because the scale has to push against you with enough force to accelerate you with the elevator. And so that extra push is going to be read in the normal force. And so it's like you feel heavier when you're in an elevator that's accelerating upward. Okay, so here we have the same situation. The guy's in the elevator, but this time what happens if it's accelerating in the downward direction? So we're going to have the same sum of the forces. The sum of the forces is going to be Fn minus mg. But here's the difference. Our coordinate system is in the normal direction. The a, the acceleration, is pointing in the negative direction. So what that means practically is that our a has to be negative. That's a little bit weird, but you can see from the picture that our a is pointing in the negative direction, so we need to have a negative a. And so basically what happens is when I solve for the normal force, the mg comes over here, it becomes positive, and I have solved for the normal force and I get that it's mg minus ma, or I can factor out the m again, and I get mg minus a quantity. So the quantity g minus a times m. And what we can see is it's as though the acceleration due to gravity has been reduced. And so the effective gravity here is g minus a, and if you've ever been in an elevator that's slowing down, you kind of feel that in the pit of your stomach, you feel lighter. And what's going to happen is if someone were on a bathroom scale, while the elevator was slowing down, or while it was accelerating in the downward direction, both of those would represent so if it was moving up and slowing down, or if it was accelerating in the downward direction, both of those would be negative accelerations, and both of those would create the same effect, that the person would seem to weigh less because of that effective acceleration. Now there's a trick you can do, because I really don't like that whole business of having to plug the minus sign into the acceleration. And the reason that I don't like that is because I've taught this for a few years now, and my students always seem to forget to do that. And so there's another way you can work this problem where you don't have to do that. You don't have to remember that the acceleration in minus. And you just have to remember one simple, easy rule that makes your life easier. And that simple rule is to always line your coordinate system up with the acceleration. So here, my acceleration is pointing down. I'm making my y point down. And so my acceleration is now pointing in the positive y direction, and I don't have to worry about making it negative. And so the same situation, what's different though, is now my mg is positive and my normal force is negative. So when I do the sum of the forces, I get positive mg minus the normal force equals the mass times the acceleration. Again, I do my algebra, I solve for the normal force, and I get the same thing that I got before. And so that's how you work elevator problems, and hopefully that is straightforward and makes sense.